Okay, great. So this is joint work with Chris Majenz, who, so he actually made these slides. Unfortunately, he couldn't be here. So the subject is quantum non-malleability and authentication. And mostly I'll talk about non-malleability. You heard quite a bit about authentication already, and you will hear more, I think. And I should say before I start that here, as opposed to the previous talk, the messages that we will consider are quantum states. Okay, so now we're concerned with transmitting quantum states. But before I get to the quantum part, let me motivate this with sort of a brief classical cartoon involving, let's say, cryptography for bank transfers in a sort of very simple idea. So suppose you want to buy a new computer, a new laptop, and something you might do in the process of doing that is send some money to the store that sells it. Perhaps by sending to the bank the instruction to transfer 1,000 euros to the notebook store. Now, of course, there could be some adversary that has access to the communication channel. And perhaps this adversary has the ability to change your message to transfer some much larger amount. Perhaps it's even the notebook store owner. And that, of course, would make you quite unhappy. So the question is, what sort of cryptographic security notion do we need in order to sort of solve this problem? Okay? So naively, you might think that encryption should do the job, that I should just make the message secret. But as I think we saw earlier in Chris Portman's talk, there are clear examples where this does not do the job, and you need some other primitive. So for example, if you encrypt with the one-time pad, it's very easy for the adversary to flip the bits of the message and change it. Okay, so one potential way to solve this problem is to use non-malleability. Okay? So what does that mean? Roughly speaking, it should look something like this. So instead of just sending your message in the plain, you should apply some transformation to it. We'll call it encryption, but in principle, it's not necessary for the result to actually be secret. Okay? So it's in this picture, it looks like the ciphertext is sort of completely randomized and the message is nowhere to be seen, but in principle, it could also be, the message could actually still somehow be visible in some part of this thing, okay? And the thing we would want from non-malleability is that whenever the adversary manipulates the ciphertext, so in this case, he manipulated it quite a bit, but it should be the case that, even if he, let's say, flips a single bit, and when the bank goes to decrypt, they should basically get just random noise, which they can then ignore. So the goal now is to somehow produce some sort of encryption that, upon any manipulation by an adversary will result in, let's say, decrypting to a random message. Okay? So no meaningful transformation of the plaintext should be possible by the adversary. So, before I get to the details of what we did, let me give you a sort of a brief summary of our results. So basically, the main result is a new definition of information theoretic quantum non-malleability. So again, the setting is we're encrypting quantum messages, and we want to satisfy something like the non-malleability notion that I described in the previous slide. One very nice thing about our definition is that it fixes a vulnerability from a previous definition. So there was one previous definition of non-malleability in the quantum case by Ambinus, Buda, and Winter. So unfortunately, it has a pretty significant vulnerability, which we discovered, but we're able to fix with this new notion. So our notion also implies secrecy. So this is kind of in significant contrast to the classical case. As I mentioned before, it's possible to have classical non-malleability where the message just appears in the plane. Quantumly, it turns out this is not the case. You have to also encrypt with secrecy. So we're able to show that non-malleable schemes can serve as a primitive for building authentication of quantum messages again. And we're able to sort of describe our notion in terms of both a simulation-based and an entropic definition. Okay? And sort of on the side, we also were able to prove something about quantum authentication, which is somewhat independent. So there was this nice new definition of security for quantum authentication by Gorjan and Majenz from QCrypt last year, which involves some key recycling, and I'll talk about that briefly. And we showed that it can actually be fulfilled with unitary 2 designs. Okay, so let's talk about non-malleability for a bit. Classically, non-malleability, as you can imagine, there's quite a bit known about it in the classical computational setting, starting with a work of Dolev, Dwork, and Nauer. who defined it in the context of public key crypto. And they concentrated on a sort of a simulation-based security definition, which talks about whether the adversary can implement non-trivial relations on the plaintext by touching the ciphertexts, basically. So it turns out it can also be characterized as a certain kind of chosen ciphertext indistinguishability. For us, I think the most useful kind of classical definition is this information theoretic one by Hanaoko et al. From 2002. And it says the following thing, okay? So now this is the information theoretic one-time setting. And this is what the definition says. It says, suppose that, consider some plaintext ciphertext pair. So X is a plaintext and C is a ciphertext. And you could imagine that the adversary perhaps even chose X and then was able to observe C. So, like in our initial cartoon, maybe the notebook store owner, managed to tell you exactly what you should transfer. And so, in effect, he chose X, and then he saw the transmission, so he also knows C. And non-malleability requires that essentially knowing X and C should give no information about what some other ciphertext will decrypt to. Okay? So the conditional mutual information of X and C tilde for any other pair X tilde C tilde conditioned on knowing X and C should be 0. Okay. Well, I mean, it doesn't have to be exactly 0. Of course, you can relax it to be epsilon, and you can do things like this. But okay, that's sort of the basic idea, right? Okay. So morally, what you should think here is that the adversary chooses an X, he observes a C, then he decides to somehow manipulate C to some other ciphertext, and as soon as he's done that, the information about what that will decrypt to is gone. Okay. Effectively, it should be random. Okay, so there's also a simulation-based definition more recently, which is also, in some sense, I guess, analogous to our simulation-based one. So here's the picture, classical still. Here's this plaintext X, our original message. It gets encrypted to some ciphertext. Then the adversary touches it somehow, changes it to some other ciphertext, and then we decrypt it to some other plaintext X tilde. And now, maybe a pictorial way to think about how these definitions are done in the classical setting is, we just have these 4 random variables. We're just going to copy them all out. We're going to put them here at the end, and now we're going to try to say something about how these 4 random variables are related. Maybe we'll say that, X and X tilde should not, satisfy any non-trivial relation, or maybe we'll just compute some conditional mutual information for those 4 random variables and, say that it should be 0. Okay? So obviously, quantumly, this is not going to work. As we all know, as soon as you send a quantum state and through some map, it's just gone, it's consumed. And so this approach doesn't really work, but of course, there is something we can do. So before I get to our definition, let me just remind you what a quantum encryption scheme is. And it's pretty basic. It's just 2 algorithms, an encryption algorithm and a decryption algorithm. So these are just quantum algorithms of some kind, depending on a key K. And you could imagine, having some special algorithm that also generates the keys, but it's good enough to just think about, let's say, a classical uniformly random key for us. Okay? Let's say some random bit string. Okay? And for us, encryption will map this plaintext space A to a ciphertext space C. The decryption map will be a little different. It'll map the ciphertext to this slightly enlarged space A bar, which is just the plaintext space together with a reject symbol. So this gives us the option of rejecting a proposed ciphertext. Okay, and of course, correctness should mean that if we compose these things with the same key, we should get the identity map on the plaintext space. And at some point in the next few slides, I'll also need this average encryption map, which just says, pick a key at random and encrypt with it, and then look at the expectation of this map. Okay? Okay, so let's start from the classical setup and sort of build up the quantum setting. Okay, so suppose, we have Alice sending the original message, Bob or the bank is the recipient, and then there's, Mallory, the malleability adversary, who will try to do some transformation on the ciphertext. So obviously, first, since we're doing quantum mechanics, we should, of course, include a reference system. So that's sort of the first obvious change. And it's also not hard to see that we should really include some side information. Okay? So Mallory could, in principle, have some piece of side information as some quantum register B about the initial plaintext and the reference. And now Mallory can combine, the ciphertext register and her side information and attack them jointly with some sort of map, some CPTP map. And the output will be some ciphertext and some other side information register that Mallory has keeping around. And then things will get decrypted. Okay, so that's sort of the picture of a sort of a one-time malleability attack. And now what we'd like to talk about is this sort of boxed map, which is what I'll call the effective map, okay, the effective attack. So this is the map that happens when, whenever Mallory applies her attack lambda on the ciphertext space, well, the effective thing that happens on the plaintext space is this lambda tilde, right? It's the map that just composes encryption, the actual attack with decryption, and actually we'll also look at the average of this channel. Okay? So lambda tilde is this sort of effective average channel on the plaintext, and the side information, of course. Okay, so what's going to be the idea behind the definition? So the idea will be to define non-malleability in such a way that Mallory cannot increase her correlations with the honest parties. Okay? So, what does that mean? There will be some, initially Mallory starts with some correlations with the good guys, with A and R. And, in the end, she also has some correlations with the good guys. And, what we want to demand is that these correlations have not increased, okay, during the attack. Unfortunately, we can't ask for this. This is impossible, because there's an unavoidable attack which you can perform on any scheme. Okay? And it goes something like this. Suppose Mallory flips a coin. Okay? And if the coin comes up heads, she just lets the state pass through. And if it comes up tails, she just trashes the ciphertext, okay? Or sends a random state in. So then it's not hard to see that if Mallory actually records the choice, records whether the coin came up heads and tails, then after the fact, she will have increased her correlations with the good guys. Okay? So this is completely independent of the scheme, and this is just something you cannot avoid, regardless of how you define things. So we basically just have to take this into account. So basically, we will allow this attack. We will allow Mallory to increase her correlations by this amount, but no more. Okay? So now the question is, if we write down this definition, is it satisfiable? And if it is, we're sort of happy, right? Because we've allowed the only thing that we've allowed is sort of an unavoidable attack. Okay, so here's what the definition looks like. So, we still have the same picture as in the previous slide. And so we say that a scheme, which is just a pair of algorithms like this, we say it's non-malleable if, for all initial states, A, B, R. Okay? So you can think here now that actually Mallory even gets to choose the initial state. She hands the A register to Alice as well as the reference, and she gets to choose what register B to keep. And for all attacks lambda that Mallory applies, it should be the case that this sort of averaged effect on the plaintext that she performs should have this property, that the correlations between her that the correlations between her final side information register and sort of what the good guys are holding is no more than her correlations were at the beginning. Okay? And as I said, there's an unavoidable attack that we have to take into account. Okay? And this is done by this binary entropy term here. Okay, so this is a little bit technical, but basically you should think that this P equals amount here is roughly the probability that Mallory decides to just let the ciphertext pass through. Okay? And then if you take the binary entropy of this, this turns out to be sort of the right way to quantify this increase in correlations. Okay? Okay, so that's the definition. As it turns out, we can also characterize it using a simulation picture, which looks something like this. So again, we're going to look at this averaged effective attack on the plaintext. And now we can say that a scheme is non-malleable if this averaged map looks like the following. It looks like a sum of two things. The first thing is something that clearly should be acceptable, which is that, that Mallory just lets the plaintext through and that does something to her side information. And the other thing is something that I think also should be acceptable, which is that Mallory trashes the plaintext and replaces it with a decryption of a random state. Okay? And then, of course, also does something to her side information. Okay? And in fact, we can give lambda prime and lambda double prime explicitly as in terms of this map lambda. So just very quickly comparing to what non-malleability was defined as before by Ambinus and Buda and Winter, roughly the picture looks something like this. There are two changes. We've added side information, which was not present before, and we made a stronger restriction on this on the sort of effective map in terms of the simulation picture, right? So previously, it was okay if essentially if this other map was a decryption of some state, and in this case, it has to be a decryption of a random state. Okay? It turns out that this difference is actually pretty significant. There's a scheme which satisfies this ABW non-malleability, but which is vulnerable to a very serious attack where the adversary can actually choose the plaintext that Bob will decrypt to. Okay? So in this case, you know, the notebook store owner could get the bank to decrypt the original message from Alice to whatever she wanted to. So not just, you know, send more money, maybe, you know, send all the money to me, you know, just a completely different message of their choice. Okay, so we were able to fix this vulnerability. Our notion is achievable. It's achievable with unitary 2 designs. So for example, if you want to implement this scheme, your key could be of something of length, let's say n squared, and then you could use these bits to generate like a uniformly random Clifford circuit, and that would do the trick. In the case of actual unitary encryption maps, our notion is equivalent to the previous one. But of course, non-unitary schemes are very interesting because they allow for things like authentication. And as I said before, we also were able to prove that non-malleability implies secrecy. Okay? So in the last minute, I will talk a little bit about how non-malleability can be used to build authentication. Okay, so this is just a little table comparing the two things. So authentication is basically a different solution to the same problem. This solution says, well, you know, whenever the adversary touches the ciphertext, decryption should just output a reject flag. Okay? So this was studied in several previous works, authentication of quantum messages. The most recent one is this Garguin and Jandry definition, which has some advantages over the previous ones. So I'm running out of time, so I won't go into the details of that. But let me, right, so as I said before, we were able to show that 2 designs are enough. So Clifford circuits are enough, again, to satisfy this kind of authentication. So in the time that I have left, so Chris Portman also showed this independently, and he might talk about this next or later today. So the proof, our proof just uses some very basic representation theoretic techniques that I won't go into. Let me just tell you in the last slide how to get authentication from non-malleability in a sort of fairly obvious way, I think. So here's what you should do. Before sending your plaintext message, you should append a bunch of zeros to it, and then you should apply a non-malleable encryption scheme. Okay? And so if you did things the right way, as soon as the adversary touches it, the decryption should become randomized. And now if you simply compare whether the final, you know, chunk of the ciphertext of the plaintext is still equal to the all zero string, that will tell you whether to accept or reject. Okay? And so we can, in fact, show that this works. So we can achieve DNS authentication using our non-malleability in exactly this sort of trick. Okay? And let me just end with some open questions. So I'll just put that up there because I'm out of time. Thank you.